I'd like to welcome you all here this afternoon. It's always a very special day for us to have this Warren Lecture in memory of one of our colleagues who passed away at a very early age in his career, Professor Robert Dexter. There's also a scholarship associated with this lecture as well. Unfortunately, the scholarship recipient isn't able to make it. He's getting married and had some details to work on for that. So the scholarship recipient, Spencer Borchert, will give him the certificate at a later date. But I'm very pleased to welcome our speaker today, Professor Gregory Deierlein from Stanford University. He has degrees from all over the United States, from Cornell to UC Berkeley, to Texas at Austin. Now he's at Stanford. We need to get him to Minnesota, the northern part of the United States. Yeah. But he is the John A. Bloom Professor and Director of the Bloom Earthquake Center there, and a member of the National Academy of Engineering, and just very pleased to have him here with us. So, Greg?
Okay. Thank you. Well, thank you, Kathy. It's really great to be here for this group, and especially for the Dexter lecture. In fact, the topic I picked today was one, simulation of ductile fracture initiation in steel structures with application to seismic design. And of course, Bob Dexter was an expert in fracture, so one of the reasons there. But I'd like to acknowledge the people listed under my name there that are former students, now faculty in their own right. And so what I'm showing today is kind of a collective effort of work that we've done probably over 10 years or so, kind of leading up to students who have just kind of recently finished, supported by the National Science Foundation and American Institute of Steel Construction and other groups. I put these couple of slides in there of Bob Dexter. It was really, I like to think of him as a gentle giant. I think he was a giant in kind of fracture mechanics and things like that. And he was gentle because as I started to get into this field, he was very kind with his criticism of what I was doing. A really delightful person who was very constructive. And so anyway, we had some great discussions back in the day. So I'm really pleased to be here to give this lecture. So anyway, I was going to talk a little bit about motivation, and then talk about these local fracture models that we're using for ductile fracture, and then show how we're using them in some applications, both to validate and then kind of looking how they're starting to be used, could be used in practice. You know, I wanted to go back, though, kind of when I first got involved in fracture, and it was when I first met Bob Dexter, was looking at fractures that happened to steel frame buildings after the Northridge earthquakes. So these were the fractures to the welded beam column connections. You know, and in retrospect, we had very high stress and strain demands on these welds. They were rather low toughness weld metals and heat affected zones. And also there were large initial built-in flaws there. Kind of a perfect storm. When I show this to fracture folks, they said, well, of course they fractured, you know. So, but that got me interested in doing kind of computational modeling of fracture. You know, and at the time, given those conditions of the low toughness and the large built-in flaws, conventional fracture mechanics, you know, stress intensity factor, we used in this example, crack tip opening displacement, where you have a discrete crack with a highly constrained crack tip. You know, these techniques worked very well to kind of simulate and predict those fractures. But one of the things, you know, one of the limitations there is when we'll do analyses and calculate these crack tip opening displacements, kind of a fracture index akin to stress intensity or J integral. And then there are tests in the laboratory that simulate the conditions at that fracture, at that crack tip. Again, they work for these kind of highly constrained conditions. And for those that aren't familiar with fracture mechanics, I think of the analogy that when we do, say, a stress analysis and we calculate stresses and keep it less than the yield strength of the material, so in fracture mechanics, we'll calculate these fracture indices like crack tip opening displacement and making that less than an analogous quantity that we calculate in the laboratory, much like we would for a tension coupon. So we did this work at the time and we're able to, for example, apply these sort of models to look at different design parameters. I won't go through the details here. These were some beam column joints, thinking at the relative strength of the panel zone to the reduced beam section to force yielding away from this welded region. And so we could build these computer models. We could look at the inelastic rotation that we would apply to these finite element models in the computer and look at the different crack tip opening displacement, the fracture demand, as a function of changes in design details. Again, I won't go through the details what the design changes were, but this was an effective tool by which we could start to evaluate design differences in design details, hone in on a design, and then do some laboratory validation testing. But the whole idea was using simulation to get these fracture indices, which using conventional fracture mechanics were fairly well established. But the limitations of the conventional fracture mechanics is it's really works well for linear fracture or inelastic, but where you have kind of limited, say, small scale yielding in the structure around the crack tip. It requires a real or presumed initial flaw that exists, so you're looking at the stress intensity or the opening at the crack tip. And they really don't work as well for cyclic loading, especially under large scale yielding, good for cyclic loading. So the thing is, after Northridge, when we started to use tougher materials and we're careful about our details, we got rid of the flaws or minimized them, used higher toughness materials. So then the question is, well, what sort of models can simulate fracture under those conditions? So it's more of a ductile fracture in a continuum. So that's really what the genesis of the work I got into about 10 or 15 years ago now, kind of working on these ductile fracture models. And the ductile fracture models are ones that could be more generalizably applied to look at still steel structures, but when we look at local buckling and tearing, things like that, to be able to simulate tearing and ductile fracture. And of course, the tragedy a few years ago on the I-35 bridge here, tearing of gusset plates, it's a sudden fracture, but metallurgically, it's more typically a ductile fracture. An example I'll show later from the damage to a building in the Christchurch earthquake. And looking ahead to the future, the way we apply these, if you go to cities, I picked on San Francisco because it's nearby. There's been, on the West Coast, and I think probably other cities as well, you know, this tremendous boom in tall buildings construction over the last 10 years. And also a Trans-Bay high-speed rail terminal coming into San Francisco. There's the skyline, if you look back over 10 years and what it's going to be a couple years from now, quite different in terms of the number of tall buildings. This is an interesting one that I happened to be on a peer review team for, a 181 Fremont, this mega brace system. Designers for this era came up with a system that's really not recognized by any building code provision, so they had to demonstrate it works using nonlinear analyses, both at the overall structural level here, looking at the structural system under dynamic loads with a combination of viscous dampers and buckling restrained braces. Actually, under very high earthquakes, the columns here will uplift a little bit, so quite a daring design. But then when you get into some of the details of that, say that this connection where these mega braces come in, doing very detailed finite elements there, because again, these things are too big to test in a laboratory, so to validate whether these things will work, that is not fracture under the applied loads. So this is kind of an ideal sort of situation where we need these better kind of ductile fracture models. So say when we look at continuum like this, what's the ultimate, you know, this material is going to yield, and we have von Mises to gauge, you know, yielding under multi-axial stresses, but what's the strain capacity, and how does the multi-axial stress state affect the strain capacity? So that's really what the models we'll talk today are all about. So the research objective we were after here is to you know, develop and validate local stress and strain continuum-based models or indices that can be applied in finite element analysis to predict the initiation of ductile fracture. And we want to specifically look at cases where we have large-scale cyclic plasticity, such that you could have under earthquake, there might be other loads, and without looking at a continuum, we're out where we don't necessarily need to hypothesize an initial flaw. So what I'll be going through is looking a little bit at these so-called micromechanic-based models, what's kind of the theory behind the equations, looking at then how we characterize those for coupon testing or material level testing, and then applying those in some experiments, some of which were designed to help us validate whether these models can really work and be applied in large scale, but then others to start to move forward to use them kind of for design and assessment of real structures. So moving ahead on the models themselves, and for folks who were in kind of fracture and material, looked at ductile fracture before, these ideas are not new. Probably like starting in the 60s and 70s, the notion of the mechanism of ductile fracture was put together, saying that if you have a continuum and you have plastic strains, we think of steel as isotropic, but inside of it there's small inclusions and so forth. But under plastic strains, you'll get kind of voids will nucleate around those little inclusions. And as you continue to strain the material, those voids will grow. And you start to get necking between the voids. So this is at a very micro level, but those that are familiar with structures, you could think of it kind of a net section sort of problem. And finally, they'll grow big enough until they'll coalesce into a macroscopic crack. So this is kind of a fairly well established for metal type structures, you know, how in a continuum, if you look inside the material, what's happening to create ductile fracture. And we can see when we look at fracture surfaces, if you look along here, looking under a microscope, it's like a cratered moon surface. You see these craters, which are the remnants of those voids that have grown and fractured. And then the question is, well, what governs the growth of these voids? We know it happens under plastic strains, but what else is causing it to grow? So to understand that, and then to say, and what's the critical radius that these voids must grow to, at which point they're going to coalesce? Okay, so there's kind of a theory that will guide us through this, and then some tests we could do to evaluate, say, what's the critical void growth. So again, those are the pictures I just showed. In fact, there's a list of people here. You could see Rice and Tracy, we were talking about at lunch. Jim Rice and a student in 1969 came up with a theory that kind of helped establish this void growth. Some of these other folks were doing experiments at the same time. But there's something we'll call a void growth index, which is equal to the integration of plastic strain. So if it's just a matter of strain causing fracture, you could kind of integrate strains till you get to a critical fracture. But then what the theory is telling us here is that, well, what's going to cause the void to grow is you have to have plastic straining, but it's going to depend on the exponential of the triaxiality. That is, this is the ratio of the mean hydrostatic stress to the von Mises stress. So it's yielding, so you're at von Mises stress level, but it's how much hydrostatic. And the more hydrostatic stress you have, say uniaxial tension on it, that's going to cause the voids to grow more as opposed to more of a pure shear type loading. So this is the essence of being able to sort of track these quantities, the multi-axial stress state and strains in the material as you load it, to integrate that overloading. And then this would be the demand, if you would, and compare that to the critical quantity. So this would be a material quantity, which would be the critical void growth index, at which point this coalescence occurs. And so ways we evaluate this and where you could see it is if you look at a tension test here, these happen to be bars that we put smooth notches in, but it could actually be a normal tension coupon where they neck down and form their own notch, if you will. You kind of load those up. We start to get kind of localized necking happening. It goes out here. And then suddenly it fractures and drops off rather quickly. And then when you look inside of this surface here, the question is going to be what's happening to that surface, what's driving the fracture. And so we need to look inside to kind of characterize the stresses and strains at that fracture location. Sometimes we'll put extensometers on and we'll say strain is equal to delta divided by the gauge length. That's kind of a macroscopic measure of strain. We want to look at the very high strains that are localizing here where the fracture is occurring. So what we'll do is then do complementary finite element analyses of these tension coupons. And so a picture is shown zooming in on that kind of notch region here, analyses that were made. And you find that as you start to load this, what's shown here on the left is a contour of plastic strain. And shown down below is the plot of that plastic strain going from the center, the centroid of that bar, out to the surface of the material. And you see there that the plastic strain is maximum at the surface of the material. So if fracture was just a strain phenomenon, you would expect fracture to initiate here and propagate inwards. But when you actually look at these bars and you see pictures like this, kind of this little cratered area in the middle and shear lips out here, the fracture moves from the inside out. So the question is, well, what's driving that? Well, if you look at the stress contour and this parameter triaxiality, again, that's the ratio of the mean kind of the hydrostatic stress over the von Mises stress, that's maximum in the center. So what the void growth index puts together is the fact that, yeah, plastic strain is driving fracture, but the voids grow quicker where there's high triaxiality, which in this case, it's much higher in the center of the bars than at the free surface out here. So when you put these together, the void growth index, as you load this, is actually maximum in the center. It's pretty flat. And so once you get the critical void growth here over a sufficient volume, it quickly propagates out. And then finally out here we have shear lips at the end as the triaxiality gets very low and you just have kind of tearing of the material. Okay. So that's kind of the essence of kind of how we could kind of infer, if you will, what's this critical void growth. we've done studies, and others have looked at, this is kind of another one of those tension bars after it's fractured, and we took a piece of the steel, and this is the fracture surface. So the one I mentioned before, if you look down at the surface, you'll see kind of like moon craters. These are the voids. And this is the material below that. And this is, by the way, on the right side, this is a computational void cell model, kind of a finite element model where we put in voids here. And an interesting thing is you think, well, as this material is failing microscopically, there should be a lot of voids growing. So even though it fractured here, why don't we see a lot of voids opening up down here? And if you look carefully, you do see some voids there. But what the test data shows from looking at pictures like this is that localization happens very rapidly over that failure surface. And in fact, we could mimic that in the finite element models to say that, you know, it's a little bit random which one of these sets of voids are going to start to neck and unload and localize. But once it starts to happen, it concentrates there very quickly, and we get that failure. So these sort of things are really made, these sort of indices are really made possible by being able to do very detailed finite element models, things with 100,000 elements, which when I started my career was impossible. And nowadays it's a little tricky, but you know, you could do it on a nice workstation. So we'll take, in doing these experiments, you could take bars that have different notch radiuses, which when you take these, they'll fail at different strain levels. So if you think of the strain at which point this fails versus this one, they'll fail at different strains. But because of the notch radius, they have different traxialities. And we could do multiple of these to calibrate this critical void growth index. And the idea is that if this theory holds up, that this VGI critical should be a material property. It's not a function of the specimen. So if we test the material and we look at multiple bars with multiple notches, or if we look at other types of specimens, that this VGI critical should be a material property, just like yield stress is a material property. And once we know that, then if we could accurately characterize the stresses and strains in our continuum, we can make a prediction of when these voids are going to coalesce and create a ductile fracture. Another aspect to it is, like, what's the critical volume over which you have to have enough voids to create a macroscopic fracture? So this shows, again, some SEM pictures we took of those surfaces, and kind of looking in from an angle, instead of looking straight down at the craters, we kind of see these plateaus here, and reasoning that kind of the voids tend to, because of the granular structure, you know, form at these different locations, and fracture occurs when these things kind of hook up and form a macroscopic fracture. And at least for the mild steel we were looking at, the critical length scale, we'll call it, might be on the order of 0.2 millimeters. That is, when you get this critical index over an area of 0.2 millimeters, or a length of that, that's enough to kind of form this macroscopic crack. And it'll start to, you know, if you continue to grow, then you'll see the crack and it'll start to propagate out from there. So that's the void growth index. And actually, folks in material science and more in the mechanical engineering, they kind of, you know, that theory was pretty well established and tested even into like the 1980s. Early 1990s, the nuclear power kind of pushed a lot of that. But it didn't deal with cyclic loading. So we've taken this idea and we want to extend it to cyclic loading. And for cyclic, we're thinking of earthquake type loading, in which case, you know, the number of cycles we get, they're very high strain cycles, but it's typically 10 to 20 cycles of large strain during an earthquake. So we coined this phrase we call ultra low cycle fatigue. Low cycle fatigue, you might be in the order of kind of hundreds of cycles. You know, fatigue, you're in hundreds of thousands of millions. So we're in this ultra low cycle, 10 to 20 cycles, and how can we extend this void growth model to cyclic loading? So one of the, you know, and so if you imagine what's happening in the material, we hypothesize, well, if under positive traxiality, that is, you have plastic strain in the presence of positive traxiality, voids are going to grow. What's going to happen, when do you have negative loading? And in a multi-axial stress state, it's a little ambiguous to say, well, what's kind of negative loading? Because in fact, plastic strain, if you load it positive or negative, that just keeps accumulating plastic strain. But we looked at traxiality as something, the hydrostatic stress component, whether that's positive or negative, we'll say, well, during that plastic excursion, will the voids grow or will they shrink? And so we extended the void growth model into a cyclic one where we keep track of the cycles during which the hydrostatic stress is tension, and we could consider that void growth a positive effect in terms of damage, and then void shrinkage over here during cycles when the hydrostatic stress is negative. So that actually recovers a little bit of this void growth. And it doesn't recover all of it, so you can put a coefficient in front. But the idea is that the accumulated plastic strain under cyclic loading would be different whether it's all tension all tension loading versus this cycling positive and negative. So the one addition beyond void growth model is to develop the cyclic demand term that distinguishes this positive and negative loading based on traxiality that the material is experiencing at that point. The other spot is, apart from the voids growing and collapsing like this or shrinking under negative loading, is that if that happens after a while, you can imagine that the voids don't purely kind of shrink down. They tend to, they change shape and they kind of collapse during the compression cycles. And you might actually start to get secondary tears in these ligaments inside here. So while the void shrinking is kind of recovering some bit of damage, there's also damage being done to the material between the linkage. And therefore, the critical value of void growth that we get from monotonic, we find we can reduce that by this function here. And this we determine really through comparison to tests, an exponential of the plastic strain, with this lambda being another material constant. And we see evidence of this if we look at the fracture surfaces. Under monotonic, we get pictures like this. And the same material under cyclic, one might look like this, where the voids are not as prominent. They tend to be smaller voids, meaning the voids didn't grow as much before it fractured and they're not as deep, suggesting, again, that this material is getting damaged between the voids due to the cycling. And by doing tests of that, we could imagine if I look at this plot here. So this would be one of those coupons where we'll do some positive and negative loading on it. And then if we look at cumulative plastic strain versus the void growth index, these zigzag lines are the demands that are coming through the positive loading, causing the voids to grow, and then the negative cycles causing them to recover some of that growth, zigzagging up like that, until it hits this dashed line, which we'll call our critical value of the void growth index for cyclic, which is the monotonic value modified by this exponential with another material constant that's shown there. And again, we've kind of demonstrated this works by doing a bunch of notched bars of the same material with different cyclic loading regimes and different notch radiuses and so forth. So this just shows a sampling of the types of tests we've done over the years, the notch bars, some blunt notch tests, some other kind of like dog bone specimens that are shown here. And then this is a plot of our measured versus predicted point at which fracture would occur for a variety of kind of different steels, again, giving us some faith in this calibration of the cyclic void growth model and the degradation, that lambda term, in the cyclic material capacity. Now, recent updates, and one of the latest students looking at that is that we previously there was an E to the triaxiality ratio in here. Actually, when we look back to Jim Rice's original paper, we found out that E to the T was really a hyperbolic sign. But folks looked at that and they expressed it in E to the T and E to the minus T because mostly we were dealing with high triaxiality cases here, so that worked pretty well and it's simplified. But actually, when we started to look at cases with lower triaxiality, we found that the models weren't working, but that's because all the papers had dropped off this term over here, so they all kind of came in this way. Looking back to the original paper, we found that from the hyperbolic sign, if we brought back all the terms, it actually came back to 0 here, so it was a low triaxiality cutoff, saying you couldn't get fracture if your triaxiality was above a value of 0. That is, your triaxiality had to be positive. So that was kind of one recent improvement to this model. Another was another stress invariant to something called the load angle beyond the mean stress, the angle here on the yielding plane. So that's another adjustment that sort of changes this. So if you have tests that have dramatically different load angles in your test, these are some variations to the demand that improve the agreement of the model with the test data a little bit more. So that's kind of where the model's at this point in time. And we've done some testing of mild steel and come up with some default parameters for this equation up here. Some of these we'd say would be default for, say, mild steel. So if we test a lot, we tend to get these as constants. But then for each material, each structure you have, you'd want to do enough notch bars where you could get the VGI critical from notch bar tests, which are pretty easy to run. And by doing a few cyclic ones, you could either take a default lambda, or if you do cyclic tests under a couple protocols, you could get this lambda that degrades it under cyclic loading. We've also done some studies that have shown that when we calculate for a material, this VGI critical, and if we look at the Sharpie V-notch values from a Sharpie impact test, that in fact there's a correlation there, which is not surprising, that would be another way to kind of calibrate these models to infer from Sharpie V-notch this VGI critical, which then can be plugged into this equation. So I'd like to, that's kind of a little background on the formula itself and the model. I'd like to look at just a couple applications, actually 3, I added one in. The first one is looking, we wanted to validate the model, and we thought what would be a good specimen upon which to validate kind of cyclic loading with large strain that wasn't too trivial. So we looked at braced frames under earthquake loading, where if you take this and you push it to the left and right, this brace will buckle and this brace will go into tension, and then you reverse it and vice versa. So you get a lot of plastic loading at the middle of the brace where the stresses and strains tend to concentrate and where fractures have been observed. So this is an example of what you might see at these locations here, both global buckling of the brace and then local buckling, and then typically fractures occurring in places like this. So we ran a test program where we looked at some different types of materials. We looked at some rectangular brace members, we looked at some round pipes, and we looked at some W shapes. And part of this was theoretical. We wanted to validate our model. But part of it also, there was debate in the steel industry and seismic whether we should ban HSS tubes because they were known to fracture. They seemed to fracture more than, for example, pipes. So for a while they were banning these and everybody was using pipes. Some people were suggesting W shapes. So we had kind of a practical reason for looking at these different sections as well. So we took those braces, we looked at different cyclic loading regimes because we wanted to interrogate the cyclic model. So we wanted to look at if we calibrated it right, it should work equally well for different types of cycling. We had to pull out coupons from these materials. So another little side study was, some of these materials are pretty thin. This might be a 1/4 inch or so. So we had to do a study of can we pull out really small, kind of thin diameter notch bars, and do we get the same answer as larger ones? And the answer is more or less yes. But the idea is we pull out these notch bars from these to characterize that VGI critical for each of the different materials. And then we ran tests. These were tests we had the opportunity to use the NEES lab at, maybe we don't have to hear that so loud. Get that out of our way. So these were this was a HSS tube. We did, I think, 4 by 4 inch and 6 by 6. So these were about 8 feet long. Let me just go back for a minute. So putting it through that cyclic loading you see over here, and we see the global buckling, then local buckling, and kind of towards the end of this you might see a fracture develop there. Okay, so we did a number of specimens here, so kind of highly controlled. And then our goal was to then make finite element models of those and see if we could kind of simulate that behavior, both at a global scale. So these are continuum brick finite elements, several through the thickness that we're modeling the overall, putting the same loading protocol. And then this is a zoomed in picture of what's happening at the middle of that brace. And you can see we pick up the local buckling and then the concentration of stresses and strains kind of in that upper corner. Okay. And this is just a comparison of the overall load deformation response, which picked up kind of remarkably well. But then what we wanted to do is to kind of look then inside the elements and say, okay, we picked up the global loading. Can we look at the local stresses and strains, including the triaxiality effect, and monitor this void growth index? So the plots on the right are for 2 different specimens, the square tube and a round tube, different cycles, and the screen didn't come through real clear, but we're looking at kind of 2 locations on these to monitor the void growth index. And of course, we'll pick the one where it's highest, and then the red lines that are shown here would be the value that we calculated from our model, calibrated to the material tests, when we would predict these braces would fracture. And we got generally good agreement. The agreement wasn't as perfect as we would like, and as we looked into it a little bit more, what we found is some of our cyclic plasticity rules, just for modeling cyclic stress strain of the material, were not as good as they could be. So the challenge with using these detailed models is not only given the stresses and strain do you want to predict the fracture, but then you need to get the stresses and strain accurately. And so that could depend on a lot of these cyclic models. And of course, from finite elements too, we know that you can get the overall behavior pretty well with finite elements, but the local behavior might not be captured as well. Okay, so we have to worry about kind of paying attention to our cyclic model, our mesh size, the geometric imperfections, and so forth to get an accurate measure of the local buckling and the strains, and then putting that into our fracture model. There were some practical outcomes that came out of this, is that when engineers saw these sort of fractures happening, they said, well, that's just happening there because of the cold working at the corner. These tubes are made out of taking a sheet of steel and bending it. The cold working, the hypothesis was it would reduce the ductility. Well, I mean, our tests and analyses clearly showed that by far it was not that effect. Rather, it was the concentration of very high strain demands that was driving the fracture in those locations. I mean, and once you explain this and look at the models, it's obvious, but it was a big question at the time. And obviously, section slenderness, which really controls a lot when local buckling happens, is a key parameter to improving, say, the ductility. And the interesting thing we found is that, at the time also, pipes were viewed, round pipes, as being distinctly better than HSS, but it really just depends on what the section compactness. We found pipes could be more fracture critical than HSS, depending on the B over T or the section compactness. So again, that was kind of dispelling what appeared to be a myth that was based on a few observations to say, well, no, if you kind of think through the problem, we could kind of reason through what are the causes of these fractures from our analyses. So that was kind of a glimpse of, kind of that one example where our goal was to take our fracture models, to take a specimen that was fairly clean. Granted, the local buckling was challenging, but there were no weldments and things like that around here. Fairly clean, and make these predictions. But then to start to use these as tools to, say, do parametric studies that could then feed into design provisions. So one part of our goal here is to develop computational tools that can augment what we do in the laboratory to help inform design. And we took this further to, say, come up with some predictive equations for what's the deformation capacity of a brace in terms of when buckling and fracture will occur as a function of the section slenderness. Now I'd like to switch to the second example where we want to look at something a little more complicated. So this was a column with a welded base plate connection here. This was the specimen. This is the test setup where all the bracing got in the way, but the specimen's buried in there. But this is one where we want to look down at the base plate where the fracture happens at a weld to see how well our models would work in situations like that. So these are the materials. So in this case, we have weld metal and base metal. We also have the heat affected zone in between the two. These are the types of materials, kind of typical structural materials, ones that we use for seismic design, so toughness qualified weld and base metal materials. We looked at the base plate connection, a standard one used in the industry, these complete joint penetration, which require this weld access hole. We also looked at a partial joint penetration weld detail. This one shown down here. This one is not allowed by the building code, in large part because you can't inspect this weld at the intersection here. They like to see this big access hole so you could get access in to inspect it. As we'll show, we actually get better behavior out of this one here. So it's a little contrary. You're building something that's inferior so you could inspect it, but you say it doesn't make sense, right? So we need better inspection or different inspection technologies. So these are the ones we're comparing. We looked at different loading protocols again because we wanted to evaluate, exercise these cyclic fracture models. So now to characterize the material here, if you think of this picture of one of those base plates, and imagine taking a coupon out of this area here, where we did this by taking a couple of plates and using the weld metal and getting the heat affected zone. That is, we made this weldment. And then we took these notched bars that I spoke of that we're going to use to evaluate the material property, this VGI void growth, critical void growth index. And we would align them such that we would put these notches. Now these are kind of gradual notches here. They're not a sharp notch. People that might be familiar with a CTOD test where you have kind of a fatigue sharp crack. These are the more rounded notches, which I like because they sample a little bit, the material a little bit more randomly. But we located these so we get just base metal. We could get just weld metal, and then we could get in this heat-affected zone. And actually, we put multiple ones in here because the heat-affected zone is kind of a vague area, you know, sectioning this out at different locations. And then pulling these bars, doing the analyses of these notch bars, and backing out this value of the critical value of void growth. And you notice up top here that the base metal and the weld metal, we got values of 2.3, whatever the units are, that's not important, it's the comparative one. But if you look at the heat-affected zone, about half that amount. And folks that do welding and things would probably tell you that's expected. You know, the weak zone is your heat-affected zone. So it's lower toughness, but also there's a lot more variability, the coefficient of variation in our measurements. So one of the things that came into this student who was working on this, his thesis, was to think about the uncertainty in this void growth index and to try to build that into our assessment procedure. This is just, again, looking at some scanning microscoped images of the base metal versus the heat-affected zone. Again, this is the lower toughness material, so the little moon craters here are smaller. So there's less, it's less tough, meaning the voids grow, but they can't grow as far before they're going to coalesce. Maybe the voids are more, whatever inclusions are there, there's more of them, or the material's tougher before it fractures. So, so again, the measurements we make at a macro level, we could kind of back up or you know, substantiate by looking at the micro level. So I'll show a little video of one of these. When we cycled it back and forth, it actually fractured down here at the flange. And this is an example of one of those. This is the flange down at the bottom. The fracture, the ductile fracture, started out here at the flange tip. And it grew for, actually the ductile fracture started back here, but it grew to the point here where kind of it tripped into a brittle fracture, where all of a sudden then this was a brittle fracture coming across, where a totally different fracture mechanism. We get that transgranular cleavage, you know, of a brittle fracture. But the idea is that the ductile fracture had to grow to, if you will, create a flaw size big enough to trigger that brittle fracture. And in fact, if you look at a kind of a micrograph of the surfaces there, if you squint here, you could see this is sort of the ductile. You see this kind of moon shape, this pot-marked kind of surface. And then this is more of the striations of the brittle fracture here, which coincided again with our, you know, you could actually see these features, you know, at a macroscopic level. This is a lot shinier here. This is kind of a grayer, but zooming in, we see these pictures. So just looking at what happened as we loaded this specimen, we got crack initiation, you know, out here at this location, at this point, and the crack initiated, or we see it on the surface here. You know, I wish we had better crack detection technologies. We basically had high resolution cameras to detect when we think this crack initiated. But then as we went along, we got total flange fracture. You know, that's when that crack would all of a sudden shoot dramatically across the entire flange. So there's a short video of this here, which I like to watch just to show how flexible steel can be. Okay, so this is a zoomed in picture. This is the flange. This is the weld metal, the cyclic loading. This is the base plate down here. That's the mill scale flaking off. And we think it's right around here that crack was initiating when we, with multiple cameras looking at that. Notice this crack is growing, even though it's visible, it's not affecting the overall load displacement behavior a lot. But then it does grow to the point it's coming up on one of these cycles where all of a sudden we'll see it gets large enough that now kind of linear fracture mechanics, you know, or more conventional, can make the prediction of at what point this will grow enough to take off and kind of have a brittle fracture. Yeah, and there we go. Okay. Okay. And the different, looking at the overall behavior that we looked at, again, for this complete joint penetration and the partial penetration, this was where fractures we think are initiating. Again, that one we looked at here was at about 3% the story drifted. It began to initiate, and it grew until 5%, at which point it fractured. But notice that the fracture initiation and this complete joint penetration are all lesser deformations than these partial penetrations. So that's kind of just a practical side product of kind of the tests we're doing to help interrogate these models. So then we built detailed finite element. We've been using kind of abacus for these, where we're using kind of a the substructure type of approach, or submodels in abacus, where we'll build a big model, and then we'll build a submodel down here, and sometimes a submodel of the submodel to get a very fine mesh down around this weld and heat affected zone. So this is kind of zooming in a little bit further there, where we'll be modeling the weld metal, the heat affected zone, and the base metal. And we do have some measurements through our notch bar test of the different stress strain properties of these materials. So that's why we're differentiating them here. And pretty fine meshes. So within each, then, we're going to track this void growth index and kind of make predictions of when the fracture would initiate. So the end result of this story, and there's a lot more details that we could spend an hour on, but this is a plot showing the void growth index as it's increasing. So this is the demand. This is the damage accumulating, say the cumulative plastic deformation. This is what we think, based on our calibration, the critical value is. But then instead of looking at discrete points, we're putting uncertainty in kind of our demands and the capacity, well, really the capacity up here. So as we cycle this thing up, the idea is when we hit this line is the point at which point we'd say fracture would occur. But we find that when you start to look at the uncertainty in this capacity here, you know, if you build that in, we used a technique, and this my colleague Jack Baker helped us with, a maximum likelihood estimate of fracture, where you're kind of accumulating the probability that you'll get fracture in any one cycle based on how close the demand is to this capacity. And here we have just a little bit in the tail. Here we've used up kind of more of that tail, and then we subtract that for the next cycle over here to make a probabilistic estimate of when the fracture would occur. So the same horizontal axis is shown here, and this is then a probability density function of during the first cycle, second, and third, when we would expect fracture. You know, so you can see the bulk of it here sometime in the second cycle. And then you could turn that into a cumulative distribution function, which just gives you the probability of failure as a function of that accumulating damage index. Okay. So the end of this story, this is an example from one of the specimens, is that this is the accumulated drift in the specimen. These black lines would be the capacity of kind of the fracture capacity, if you will, that's being developed in the different materials based on what we saw in the different heat affected zones we made and some of the base metal that was tougher out here. And of course, there's variability in that. And then when we take our maximum likelihood, this probability then gives us our maximum likelihood estimate. So the estimate would be that this location would control as being the most critical. You know, and if we're at a certain amount of accumulated drift, we'd have a certain probability of fracture in this location, that location, or the other. And we tended to find fracture in our specimen kind of in this region here. Again, that fracture kind of grew slowly there. So again, we can't, unfortunately, get a really precise, you know, this is exactly how things correlate, because getting the properties of the heat affected zone is anything but a precise science, but a probabilistic estimate of the fracture. The last example I wanted to show quickly, this is something that actually I was not directly involved with. One of my co-authors, Amit Konvinde, who's at UC Davis now, worked on this. After the Christchurch earthquake in 2011, there was damage to this parking garage, which the lateral system consisted of eccentric braced frames where this fracture was observed. So Amit saw it as an opportunity to, again, exercise these models, and also NSF exercise their rapid response after earthquakes to learn from them. So in those who aren't familiar with these eccentric braced frames, they're a seismic system that under lateral loading, they're designed to dissipate energy in these link locations here. So to purposely avoid brace buckling and to concentrate the inelastic deformations in the link, but hopefully these are ductile enough that they don't fracture in the way we saw. So Amit and his students, they got plans for the parking garage, built computer models with open Cs. They had some recordings from nearby ground motions from the 2011 earthquake, ran these through the building to get global deformation demands on these braces, on the brace bents here. And then they fed these into We don't have to see the whole thing there. Into detailed abacus type models of the type I showed. They had also gotten some samples of the material sent over here, so they did the same set of notched bars, to calibrate the critical value of the void growth index. Built abacus models and kind of ran them through, and again, they're trying to predict the fracture over here. Now, one of the things that was a subject of debate, I'm not sure if it was litigation or just debate, was that this structure was not built exactly the way it was designed. It was designed where these brace elements here would have a stiffener plate and they'd align right at that point. Well, on this side, they were a little bit off. Okay, you can see the brace comes in a little bit off from the stiffener. And so you would say, well, that's going to sort of concentrate strains there. But there's still the question, well, how much does it concentrate the strains to drive the failure? Like, how much worse is this side than this side over here? So we applied the same model I'm talking about, the cyclic void growth model. And in fact, when he looked at two configurations, one is if he looked at a perfect joint that didn't have that little offset, the ideal condition, and one is he looked at it as constructed with that little built-in eccentricity, and these were seconds into the earthquake that he makes a prediction of the fracture index. This is the void growth index, so the value of 1 is when it reaches its critical point, predicting fracture at 20 seconds into the earthquake. Now, we don't know, this earthquake was around, I think the strong motion was about 3 times that length, so we don't know if he got it right, if it fractured at 20 seconds or 30, but it did fracture, and granted, this is a retrospective, but this just shows some of the ways you could start to utilize these models, and this showed kind of the influence of both stiffener misalignment and just the intensity of shaking. This building, by the way, had seen the earlier earthquake. If you remember, the Canterbury earthquakes were a sequence that started in September of 2010, went to 2011, and the devastating one in February. So this lived through the first one, so he could do analyses of that, and then it was in the larger second one, the larger intensity, where we saw this, where all the damage occurred and fracture here. So I think these models are kind of promising, but there's some challenges and limitations. First, in order, because they are local models, and I think folks that have studied fracture for 100 years, could imagine things like this were happening. But until recently, we have no ways to accurately characterize the stresses and strains at a very local level. You really need these detailed finite element models, and you need the computational power to run these models with 100,000 or more elements, because you need pretty fine models in there. So now that we're able to do this, but we still need high fidelity finite element to capture, in the case of the braces, we need to get the overall deformations right, and the local buckling that's happening there. And also, as I mentioned, things like cyclic plasticity need to get all of those pieces right to make accurate predictions of the stresses and strains. One of the challenges to doing that, by the way, is kind of this non-uniqueness problem, and just that when you're kind of calibrating these plasticity models, you could take your stress strain coupon of the material, build a plasticity model, build the abacus model, and think you have a good answer here because globally you have a good response. And you could look at the deformations of local buckles. Maybe you could make some measurement of those deformations. But the idea is different parameters can give you the same result. So there's kind of that non-uniqueness on these reverse problems, and the problem is it might affect, you need to look how the differences might affect the local stresses and strains and carry that into your fracture prediction. And then there's additional problems, the randomness and material properties. I mean, we made a start on it, but I think there's certainly more work to look at the uncertainty, the variability, propagating that through. We've just really looked at fracture initiation, and as you saw in some of those examples, real bad things don't happen until the crack grows far enough. So we haven't taken this to the next stage to really apply them to crack propagation, and also then to look at the transition to that brittle cleavage fracture. Is it as simple as saying, you have a critical crack length, and when the ductile crack goes that long, you transition to brittle cleavage, or is it more complicated than that because you are deforming this material? So just concluding remarks is that I think the examples I showed from these tall buildings that are happening, special bridges, Ted Galambos' famous favorite architect, Frank Gehry, when he comes up with designs, the engineers are challenged to come up with structures for these. Oftentimes they're building things outside of the building code realm. So having tools in practice where people could build these more advanced, elaborate structures with confidence, being able to really simulate and check these failure modes. So I think that's the motivation. We need better scale, the reliable scale of the material scale phenomenon, getting down to accurate stresses and strain. This field, as I mentioned, a lot of Jim Rice's paper from 1969, it's been around a while, so on the one hand it's pretty mature, but filling in all the details and getting the parameters and building up a lot of confidence in it, there's still plenty of work to do there. And I think finally, whether one attempts to do this, in research we'll try anything, but in practice, it's looking at the practicality and the accuracy, not every problem is going to be made for solving it this way because it's not trivial. But when the problem warrants it, I think the tools are there that people could start to use these with more confidence. So with that, I'll wrap up and thank you for your attention.
Very nice talk. I'm intrigued about your stochastic finite element modeling. When you get the fragility curve, it seems that the element size is extremely small in your model.
Yeah, yeah.
And how you deal with autocorrelation lengths for the spatial randomness of VGI critical?
Yeah. So what we're doing there, we did some, well, first how we characterize the material, like in the heat affected zone, we put those notch bars through the area we thought to be the heat affected zone. And then we tested those and analyzed those and backed out a fracture index. So we got a distribution of that critical fracture index and the dispersion on that. So, and then we would take that as given, and then in our models we would, I guess the demand we were calculating was in a fairly deterministic fashion. So we were calculating, we take one mesh and typically, if you don't have a sharp crack existing, the stress and strain gradients are gentle enough that even though they look sharp macroscopically, when you look compared to the critical length of 0.2 millimeters, they're pretty gradual. So we felt we could kind of sample. We didn't have really a sampling problem, we think. So we would just kind of, our element size might be on the order of 0.2 millimeters and kind of sample it at that level. So the randomness was really just all in what we considered to be the capacity of the material. Yeah.
Oh, I'm fine.
All right, actually, they want to record.
That's for the recording, for posterity.
Hi, my name is Victor Schneer, and I have a quick question for you. In your presentation, you basically concentrated on welded connections, not so many examples with bolted connections.
Yeah.
Do you have any experience or any suggestions to share?
Yeah, well, we've thought about these models could be applied to a bolted connection. And you'd say, well, why would I do that? Because we kind of like our design models, to look at net section and a thin plate. They work pretty well because, if all bolted connections were thin plates with not too many bolts, the net section works well. But suppose you have a really long bolt group, where there's unequal stresses going through it, and suppose you start to have a pretty thick plate where the stresses and strains aren't the same through the plate. And, and frankly, I think we assume our design provisions, they've been tested on small things in the lab, and then we use them for massive structures with, Paul, you used to design things with 4-inch thick plates with bolted connections. So I think these models are ideally suited to that because those are cases where you tend to have ductile fractures. And you'd have to, though, build a finite element model that represents the geometry with the bolts and even getting the friction right, clamping and so forth. So if you could build the finite element model, and calculate the stresses and strains, this void growth model would give you a way to reason when you would start to see ductile fracture initiate. Yeah.
Thank you.
Okay.
Other questions?
My question is about your model. Do you expect then any void growth at zero triaxiality?
Right. So so one of the things people debate on these models, if you read papers, is where's the triaxiality cutoff? That is, where's the the lowest value of traxiality at which voids won't grow and fracture won't initiate in the mode that's shown here. And so we've looked at tests and data, and we like going back to Jim Rice's paper, the fact that if you put the full function in there, it cuts off at 0. So our presumption would be that's kind of the cutoff. That is, if you have plastic straining in the presence of 0 traxiality, you'll have no significant void growth and no tendency for these types of fractures. Now, it brings up, though, that there's, this is one mode of material fracture, this void growth. If you say, well, can you take the material and just infinitely shear it? The answer is no, but there's another mechanism at work there, which this void growth doesn't exist. So as you go down, just like if you get to a very sharp crack with a low toughness material, you might find that brittle fracture will occur before void growth. So I think, and others have said this too, like the cutoff for ductile fracture is around traxiality of 0. Some say 0.2, but we like the value of 0 because frankly, there's not a lot of data down in that area.
Other question? Well, again, thank you to our speaker, and we're going to have a reception now.
Okay. Okay. Oh, thank you.